My name is Eugene, and I'm going to talk about our recent work in LTE in the unlicensed spectrum. So first question here is, why do we actually need LTE in the unlicensed spectrum? And the answer to that largely is because we need bandwidth. And bandwidth for a lot of new applications, augmented reality, VR, games, and streaming a video. So all this will require more spectrum, more bandwidth, need more capacity than what we could easily get on the existing LTE infrastructure. And the most cost-effective way of increasing the bandwidth that we actually have now is to take whatever we have now, the existing LTE infrastructure, and add unlicensed spectrum to it, a spectrum which is essentially free, and you get essentially improve the capacity of the LTE network. However, obviously, there is an ongoing argument, or I would say a discussion between LTE and Wi-Fi regarding, firstly, what's the best way for LTE and Wi-Fi to coexist on the unlicensed spectrum. And when I say unlicensed spectrum, I mean ISM bands in the 5 gig ISM bands. And the other one here is, should LTE actually be allowed to be doing this? So before we actually go into try to answer any of that, we should cover exactly what I mean by unlicensed LTE. Now, unlicensed LTE is an umbrella term, largely an umbrella term that would refer to two kinds of LTE operation in the unlicensed bands, in the ISM bands. So the first one is LTE unlicensed, or LTE-U. So this is industry proposal, not standardized by 3GPP. And what it has here is that you have an LTE, a regular LTE spectrum, LTE channel on the licensed band. This serves as your anchor band. And along with that, you have an identical LTE channel, LTE specification that runs in the unlicensed band. Now, in the unlicensed band here, we cycle this LTE channel on and off, depending on the cost timescale load that we find, cost timescale Wi-Fi load that we can find on the unlicensed ISM band here. Now, the other one we have is what is known as license assisted access, so LTE LAA. Now, LAA and LTE-U share the design for these two are common in the sense that both of them have a licensed anchor band in the licensed channel. But LAA uses what is known as listen before talk, LBT. So it operates slightly similar to how Wi-Fi CSMA would work. LTE would sense the channel. If Wi-Fi is not there, it will grab the channel and transmit. The other big difference here is that the transmission burst of LTE LAA tends to be a lot smaller than LTE-U. So it varies from 1 to, I think, about 10. Okay, so the big issue here with coexistence between Wi-Fi and LTE comes down to actually the asymmetric channel sensing capabilities of Wi-Fi and LTE. Largely speaking, LTE, even if you use LBT and everything else, uses only energy sensing to determine Wi-Fi activity on the channel. Wi-Fi uses preamble and energy sensing. So the result of this here is that LTE to Wi-Fi sensing ranges tend to be shorter than Wi-Fi to Wi-Fi. So LTE, even if it operates according to spec, everything is going well, it can still kill the Wi-Fi access to the channel because it simply is not aware that Wi-Fi is actually there. So in our measurements, we have some test bed evaluation in NEC, and we can show here that even when the SINR of Wi-Fi, in our test bed here, we have one LTE link, one Wi-Fi link, both of them operating in a 5.2 gig band. Even if the SINR at Wi-Fi is high, the existence of LTE can reduce the Wi-Fi throughput by a substantial amount. The reverse is also somewhat true. You will have some impact of Wi-Fi on LTE. Impact tends to be smaller because LTE tends to be more resilient to interference and noise. It's a good and bad thing. Bad in the sense that Wi-Fi does have an impact on LTE. Good, good or bad or whatever. But at the same time, you have the case where LTE may not actually be aware of Wi-Fi even if there's some degree of interference. So if you use LTE's performance to estimate the existence of Wi-Fi, things could go quite badly. One simple, straightforward way of solving this problem is to simply combine LTE and Wi-Fi. I mean, we have Wi-Fi now, we have LTE. If we merge the two of them, the problem largely would go away. But the issue here is that this is not exactly a very popular approach because obviously, it creates a dependence between LTE and Wi-Fi. And so LTE specification, if we merge the two of them, LTE specification would now be dependent on Wi-Fi, while Wi-Fi is free to do anything it wants. And obviously, it's not an easy way to manage the LTE specification, and both the operators and people who create the hardware are not fond of this approach. The other way here is to simply lower the energy sensing threshold that LTE uses. So there's some work on LAA to achieve this, but the downside to this is that if it's not done carefully, you got a case of increased false positive because of LTE. So it might help Wi-Fi a bit, but it will kill the LTE performance. So we are trying to find something that solves this issue without having to harm LTE. So largely, what do we actually aim to do here? If you don't remember anything that I talk about after this entire talk, because you are forced to be here, so just remember this, that our work, we aim to provide Wi-Fi awareness to LTE without the problems of Wi-Fi dependence. So the solution that we have here allows LTE to communicate with Wi-Fi, but we don't require hardware changes. We don't require any changes to the PHY, and most importantly, we don't actually require any changes to the specification. And we call our solution ULTRON because we are strangely big fans of Marvel. Okay, so now that we have covered the introduction, a bit of design, as much as I can get into this. So the target for ULTRON here is a dual interface small cell. And what I mean by dual interface small cell here is that we have two interfaces on the small cell. One of them is LTE. It can support up to 5 channels, or in LTE terms is component carriers. So 5 channels, up to 20 megahertz per channel, so about 100 megahertz in total. And you also, on the other interface you have on this small cell here is a Wi-Fi small cell, Wi-Fi interface. One single Wi-Fi interface, one single LTE. And we have 2 big components in this ULTRON design. First one is what I call CTS-EMBEDDING. So it allows you to embed CTS signals into an existing LTE protocol with no changes to the LTE PHY or the hardware. And the other one is scalable sensing. Essentially, CTS-EMBEDDING is the mechanism, scalable sensing is the policy here. How do we actually decide when and how to perform CTS-EMBEDDING? And that is what we have for scalable sensing, interference-aware LTE traffic scheduler. Now, how does CTS-EMBEDDING work? So if you remember earlier the diagrams, LTE-U and LAA both have got bursts of transmissions on the unlicensed bands. So in CTS-EMBEDDING, the first subframe of every burst, we replace it with a special LTE frame that contains your CTS, your embedded CTS. In that particular subframe, essentially the CTS is carried in the first OFDM symbol of the data portion. You have 2 configurations here because there are some configurations of LTE where you don't need the channel, control channel. The PDCCH that you see in front here is the control channel. Some configurations don't, and that would actually reduce the latency at which your CTS can be transmitted. And we reserve, so the CTS is used actually here to reserve a channel. We reserve the channel by changing the nav field in the CTS to be equal to the length of time the LTE is going to use the channel for. Okay, so I'm going to reinforce here that this entire process does not require any changes to the PHY at all. It does require changes to the scheduler. However, the scheduler is typically a software-based thing, and schedulers are not part of the LTE standard, if you can believe that. And the other thing is also that we only go for now, we're going to target this to a downlink-only example, just to make things clear. Now, the part you were interested in here is the MAC and the PHY. MAC tends to be in software. This portion of the PHY here is in the hardware. And largely speaking, the scheduler would create a transport block, which is the LTE version of the Wi-Fi PDU. And it goes through the entire PHY, and whatever comes out at the end gets transmitted over the air. The exact process in which we embed this CTS can be a bit complicated, so the details are in the paper. But at a high level, what we essentially do here is that ULTRON would determine this. We would find out the bits that would need to go in the transport block, such that after the transport block goes through the entire PHY here, the output we get here would be equal to the CTS that you would see from a regular Wi-Fi transmission. To be precise, the transport block, the CTS that comes out of one transport block actually goes into one portion of the entire LTE subframe. So the entire CTS would involve encoding multiple transport blocks, and ULTRON would find out the correct bits that you have to put in every single subframe. Scalable sensing. So if you recall earlier, I mentioned that we target a dual interface small cell, and we only have one Wi-Fi interface. So the objective of scalable sensing here, one of the objectives at least, is to figure out, number one, how to best use this single Wi-Fi interface to scan across up to 5 LTE channels and to figure out the Wi-Fi load on them and what the appropriate amount of LTE load you will have to put on each of the channels. So, and that's what the interference and assignment and traffic allocation is for. We have to scan each of the channels, not always in order. And we have a joint optimization problem to solve this in a unified, optimal way to figure out at any one point of time, the optimal location for the Wi-Fi sensor and the amount of load that we place on all the 5 component carriers. Okay, so a bit of evaluation here. Okay, so when we are evaluating this platform, so we have, we evaluated this in a real-world experiments using a couple of USRPs. So we have got one INOB, which we place at the orange location, the orange mark that we have there. That's where we locate our INOB. Excuse me. And the rest of the gray points is where I place the UEs, the APs, and the Wi-Fi equipment. Now, the LTE transmission that I use for this evaluation is slightly different from the existing LTE transmissions you would see elsewhere. That's because in LTE-U and LAA, one of the things that we need to do here is to be able to decode the LTE signal at arbitrary points in the entire transmission. This is not actually possible in current LTE transmissions because we only have synchronization signals at fixed points in the LTE frame. So a simple modification here is that we change the LTE subframes to include the PSS and SSS, what is known as the primary and the secondary synchronization signals for every transmission, and that allows us to decode LTE transmissions, if they exist, anywhere within the LTE transmission stream. Okay, so the accuracy of our CTS embedding, surprisingly, it works well. In our test bed, so what we do here is that we place the INOB there. Oh yeah, I forgot to mention this. So the Wi-Fi that we use here is warp-based Wi-Fi, and for larger scale emulation, because we only have a limited amount of hardware for over-the-air measurements, so for larger scale experiments, we will rely on emulation. And what am I doing? Okay, sorry, for ULTRON. Transmission. Every transmission burst of ULTRON is between 1 and 4 subframes, and between every subframe, every transmission burst, I have a backoff about 1 millisecond. This is in a way trying to emulate LTE-U and LAA operation. Now, so CTS embedding, we place the INOB at that point there, the yellow point, and I move a Wi-Fi node all around the entire test area. And we have found here that even if the energy, the receive energy at the Wi-Fi receiver is slow, we get about 95% decodability in our embedded CTS frame. So what this essentially means here is that we can effectively embed Wi-Fi CTS into LTE with no changes to LTE, and we can use that to tell Wi-Fi essentially to back off. The obvious benefit of this is that once Wi-Fi backs off, it will eliminate the collisions between LTE and Wi-Fi, and therefore it prevents LTE from killing the Wi-Fi throughput completely. Benefits of CTS embedding. So we did a larger scale experiment. Again, we have a number of UEs, one INOB, a number of UEs, and four Wi-Fi links around. So we have found that in our experiment, in various topologies that we have in our test bed, we can improve Wi-Fi throughput up to about 4.5% compared to the case where we operate LTE and Wi-Fi and we don't have CTS embedding. And at the same time, we improve Wi-Fi throughput, but we also do get an improvement in LTE throughput. And this largely comes from the fact that Wi-Fi will have an interference impact on LTE, and if we eliminate the LTE, the Wi-Fi interference, both of these would actually gain. Both LTE and Wi-Fi would stand to gain here. Now, when we have ULTRON on a larger scale here, we obviously can't do it in our real-world evaluation, so we simply emulated it. So I emulate this, I compare the performance of ULTRON to 3 other cases. The first case here is the performance upper bound. Essentially, we take the same protocols, but now instead of having only one Wi-Fi sensor, we have one Wi-Fi sensor per channel. So what this means here is that you always have a global view of Wi-Fi activity on the channel. Second B, what I call B here, is that essentially what we have here is B is used to highlight the benefits of properly allocating LTE traffic on the Wi-Fi channel instead of simply blasting as much as you can on the channel that is most free. And C, the option C, Max Wi-Fi, is comparing it to Max Wi-Fi is aimed to, the goal of it is to show the benefits of the proper placement of the sensor, the Wi-Fi sensor, the one Wi-Fi sensor we actually have. So one note here is that always placing the sensor on the node which either has the least or the highest Wi-Fi activity is not always the optimal case. So we have got gains for both LTE and Wi-Fi. So when we compare LTE to option A, we can show that overall ULTRON does achieve close to the highest performance in both Wi-Fi and LTE. And when you compare it to option B here, then you can see here that ULTRON's traffic allocation is fairly optimal. So we get good Wi-Fi performance, while the LTE traffic here is also performing quite well. And for option C, we can show that we demonstrate here the importance of correctly placing the Wi-Fi sensor, the one Wi-Fi interface across the 5 LTE component carriers. So, as I mentioned earlier, if you don't remember anything that I've talked about, just remember that we have Wi-Fi awareness here with no Wi-Fi dependence, and our solution is called ULTRON. 2 big components that we have here is Wi-Fi embedding and Wi-Fi sensing. Thank you very much.